page 2 of your oscillation worksheet, there's one question that we can actually do from here, right? So state what is meant by simple harmonic motion. This is June 15 P42. Let me just open up the pause here from there. Okay, now simple harmonic motion, we already know the definition. That was something that we covered in the lesson last week. It's just periodic motion in which acceleration of the body is directly proportional to its displacement for a fixed point, and the acceleration is always directed towards that point. Okay, this is the definition that you can actually just take from the notes. But if let's just say you kind of couldn't remember how it was actually worded, you can actually break it down into very two simple sentences. The marking scheme just really wants to see that you say that acceleration is directly proportional to displacement. This is one. And that acceleration and displacement are always in opposite direction. This is another point. Okay. So if let's say you have trouble trying to recall how it's actually worded, you can actually just break it down into very two simple sentences. Acceleration directly proportional to displacement, and acceleration and displacement are always in opposite directions. Okay, so that is for definition of SHM. Now for part B, they mentioned to you that the variation with time t of the displacement x of two oscillators P and Q are shown in figure 4.1. So you have two oscillators. Oscillator P is this orange colored line here. That one is the dotted line. Sorry, this one is the solid line. So sorry. This is oscillator Q, sorry. This one is the one with solid line. Oscillator P is the dotted line in pink right here. Okay, you have two oscillators, and what you are having here is a displacement time graph. So they tell you the two oscillators each have same mass. Find out the phase difference between the two oscillators from the given figure. So this one, finding out the phase difference between the two oscillators is something that you guys have learned in AS physics waves, okay? So when it comes to finding phase difference between two waves, you always need to pick two similar points and then compare with respect to one full cycle. So if you try to see the diagram right now, this is considered one full cycle. Okay, so this is one full cycle. This is actually t equals to 1.2 seconds. Then after that, what you're just left to do is to find two similar points. So an easy point to pick would be the crest position or the amplitude position. So if I pick the amplitude position for oscillator Q, I should also pick another corresponding crest position for oscillator P. So I find the difference between them, which in your case, if you try to find the difference between them, it's actually going to be 0.2 seconds, right? So from here, you want to find the phase difference. The phase difference is really just going to be 0.2 over 1.2. Okay, 0.2 over 1.2. This one is actually the fraction in terms of a cycle. But we know that one cycle is actually 360 degrees or 2 pi radian. So here I can actually just replace it as 0.2 times or 0.2 over 1.2 times 2 pi, eventually giving me the answer of 1.05 radian. Okay, this is what answer for part 1 is. Okay, you can actually also kind of write it in terms of fraction, 1 over 3 pi radian, but I actually won't advise it because sometimes when students write the answer in fractions, the marking scheme don't accept. Now, sometimes when they write it in fractions, they accept. So it's a bit ambiguous. Sometimes they do accept, sometimes they don't. To be safe, just write it in numbers now. All right. Okay, then the next one we'll be talking about what is the maximum acceleration of oscillator Q. Okay, they want you to find out the maximum acceleration of oscillator Q. So keyword maximum acceleration. Okay, so since this is an oscillation kind of question, even though they never mentioned to you that this object is undergoing simple harmonic motion specifically, is implied to be simple harmonic motion because you see they already asked you to define SHM in the first part. Okay, so you assume that this object is actually moving with simple harmonic motion. So when it comes to maximum acceleration for simple harmonic motion, A is omega square x naught because it came from A negative omega square x. Okay, the equation for acceleration just now was this one. So you want to find A max, it will be omega square x naught. Okay, you just replace x with x naught because that's the point where acceleration is maximum. Okay, and you might also notice that there's a negative sign before this. The negative sign here you don't need to consider because just now I mentioned to you for calculations, negative sign can just be omitted. Okay, I think I did mention it somewhere here. Yeah, negative sign can be omitted during calculations of V and A in questions. We're really just interested in the magnitude. So negative sign, just get rid of it. All right, don't need to bother writing it in. So A max is equal to omega square x naught. Now omega is not given directly. You have to calculate it out. Omega is 2 pi over t or 2 pi f. The omega here is referring to your angular frequency. Okay, so either it's 2 pi f or 2 pi t, 2 pi over t, sorry. Here you can actually find out what is t. You actually did kind of find it just now when you were trying to do the phase difference question. So you've already found out that t was actually supposed to be 1.2. Okay, if you try to draw a line from here all the way to here, t is actually going to be 1.2 seconds. Okay, from there you can actually find out your omega, right? So it is 2 pi over t squared and then multiply with your x naught. Your x naught is your amplitude. Okay, but which amplitude should you take? You should take the amplitude for oscillator Q. Okay, they specifically told you to use oscillator Q. So oscillator Q is the solid line, which is the orange colored line that I just highlighted here. Your amplitude is actually 3 centimeter. Okay, so 3 centimeter is actually your amplitude. So sub in your values, eventually you're going to get the answer as 0.822 meter per second. Okay, this is actually one part. Then next question that I'll move on to is find out the ratio of the maximum KE of oscillations of Q to maximum KE or oscillations of P. Basically find out the ratio of maximum KE of Q to P. Now in the notes just now I mentioned to you that maximum KE is half m omega square x naught square. All right, which is in this part. Okay, half m omega square x naught square. This is your maximum KE. Right, I told you total KE is actually your KE max. So KE max is also total KE. Here I wrote here total KE. Total energy is half m omega square x naught square. This is actually also your maximum KE. All right. So if it comes to ratios, you know that maximum KE equation applies to both Q and P. One is constant between both of them. You can actually try and see. The first thing is that the mass is actually constant because the question specifically told you the two oscillators each have same mass. So M is constant. And then when you look at your graph just now, for oscillator P and Q, your omega is actually supposed to be constant too, because you see omega is 2 pi over T. If T is constant, omega is going to be constant. So when you look at your graphs for P and Q, this one is the period of oscillator Q. This one is the period of oscillator P. By right, they are always if you try to see the period, this one will be 1.2 seconds. The period will be 1.2 seconds for the pink line. It will also be 1.2 seconds for the green line. Okay. So both of them have the same period actually for oscillator P and Q. So obviously the omega will be constant. Okay. So M and omega are constant. Therefore, Ke max is actually just proportional to your amplitude square. So the ratio of maximum K of Q to P is just the amplitude of Q square to amplitude of P square. So ratio is thus 3 square to 1 square. 3 centimeter square to 1.7 centimeter square. Okay. You can see you can get the amplitude readings from the graph itself. Okay. Now there's no need to change the units from centimeter to meter, because you see it's ratios. Your units actually will cancel off. So if centimeter you square is centimeter square, divide by centimeter square also, the units actually do cancel off. So there's actually no need for you to change to meter. All right. So your final answer will actually be 3.11 for the ratio. Okay. So this one is okay. Okay, so that one is done. Now use data from B to sketch on the axis of the figure below the variation with displacement x of acceleration A of oscillator Q. They want you to plot a graph of they want you to plot a graph of acceleration versus displacement. Okay. So just now I mentioned to you that if your acceleration is A negative omega square x, you equate it to a straight line equation, you're going to get a straight line graph that passes through the origin, isn't it? So straight line graph that passes through the origin with negative gradient. This one will be your graph of A versus X. Okay. So when they ask you to plot a graph of A versus X, now you know by right it should just be this particular graph. Okay. It must be a straight line graph through origin with negative gradient. Okay, so in your case here, when you want to plot the graph, the negative is actually very important to take into account. Okay, that's why just now I mentioned to you the negative sign, if any, is usually only for your definitions or graph plotting. So in your case, in your graph plotting, your negative is actually pretty important to take into account. All right. Now, your question also specifically asks you to make use of your data from B, you see. Your data from B was actually your A max equal to 0.82 meter per second. So let's just say for the sake of simplicity, I just say as 0.82 meter per second square. So what you're supposed to do is that you're supposed to indicate the values of the A max at the respective amplitude. So A is max when X is at your amplitude position, which is 3 centimeter. So what you're supposed to do, in addition to having a straight line graph to origin, is that you need to mark out your points. So at the 3 centimeter position, positive, negative 3 centimeter position, you're supposed to mark out your A max. Okay, you're supposed to mark out your A max, right? So try to draw the thing to scale. So you can actually say that this one is 0.5, this one is negative 0.5. I can say that this one is 0.5, negative 0.5. So this one here would actually be positive 0.82. This one will be negative 0.82. Okay, so just make sure you draw the thing properly to scale and you should be okay, right? So that's for this question. Now next one would be page 6. Okay, so if no problems with this, we'll move on to page 6. Now let's have a look at page 6. Okay, page 6. This one, November 15P43. Okay, now you again have that same definition question where you're asked to define simple harmonic motion. Just copy the definition from the notes. Periodic motion in which acceleration of the body is directly proportional to displacement from a fixed point, and the acceleration is always directed towards that fixed point, worth 2 marks. Okay, and again, if let's just say you've forgotten how to word it properly, you can always just say acceleration is proportional to distance or displacement from fixed point, and acceleration and displacement are always in opposite directions. Okay, either one will do. Now, part B kind of relates to what you have learned in AS physics before. So they mentioned to you, let me just zoom in, sorry. They mentioned to you that you have a tube that is sealed at one end that has cross-sectional area of 4.9 times 10 power minus 4 meters square. Some sand is put in the tube so that total mass m on the tube and its content is 70 grams. The tube floats outright in a liquid as shown. The liquid itself has density rho equals to 0.79 grams per centimeter cube. Now, by reference to the liquid pressure exerted on the base of the tube, show that the distance h on the base of the tube below the liquid surface is 18 centimeter. Explain your working. Okay. So here specifically they ask you to use liquid pressure exerted on the base of the tube. Refer to the liquid pressure exerted on the base of the tube. Okay, so this one kind of relates to your AS last time. So you see, if I have something that's being submerged inside a liquid, if I just consider one particular depth below the liquid, I can say that the pressure at point A is the same as pressure at point B. Okay, pressure at A is the pressure due to the liquid. Pressure at B is actually the pressure due to the tube. So this one is pressure A equals to pressure B here now. Now pressure due to a liquid, I can actually just straight away use H rho G. Okay, pressure due to a liquid is straight away just H rho G. Now pressure due to the tube, because it's considering the weight of the tube acting on the area of that liquid, pressure is force over area. The force here is actually the weight of the tube. So I can actually say pressure here due to the tube is mg over A. That's why you have this thing here. Okay. Then after that, it's a simple matter of you just cancelling whatever is not necessary here. The g's will cancel off. Eventually, you get h is equals to m over rho A. Now you know the value of big M, which is 70 grams, changed to kg. You know the value of the density is 790 kg per meter cube. Your area is 4.9 times 10 power 4. Eventually, you get the answer as 0.18 meter, change it back to centimeter. Okay, now your density is not given in kg per centimeter cube. Instead, it was given in terms of grams per centimeter. You have to change it to kg per centimeter. You have to change it to kg per meter. So 0.79 grams per centimeter cube is the same as 0.79 grams over 1 centimeter cube. So you change the gram to kg, divide by 1,000. We change the centimeter cube to meter cube, you times 10 power minus 6. So eventually you're going to get this answer. Okay. So 1 centimeter cube is the same as 10 power minus 2 cube. That's why it's going to be 10 power minus 6 meter cube. All right. So you're going to get the answer as 18 centimeter eventually, once you do the complete substitution. All right. So this one should be okay. Okay, so no issues with this. I'll clear off the diagram and move on to the next page. Okay, next page would be this one. Okay, so for this one, they tell you the tube in B is displaced vertically and then released. The variation with time t or the distance h is as shown in this figure. So the system oscillates with simple harmonic motion of angular frequency omega given by this expression here, where g is the acceleration of free fall. Use data from the table to, use data from B to determine time t1, time t3. Okay. Now, in your case, when you look at this graph, this one is showing the oscillation of your tube once it's been displaced from rest. They want you to find out in the first place what was T1 and what is T3. Okay, what was T1 and what was T3? So there's some relation you can actually see from here. If you look at the graph, this one is actually kind of like displacement versus time. Kind of like that, but it's actually not your displacement versus time. Okay, you get the reason why later. So here, the pink color section that I highlighted to you is actually one period. This one here is actually one period t. Now t1 is actually just half a period. If you see from here, t1 is actually half a period, whereas t3 is actually 1.5 period. Okay, t1 is half a period, t3 is 1.5 period. So if only you can find out the period, you can then find out what is T1 and T3 then. All right. So here, what you can do is you make use of the equation that has originally been given to you to find out what is T. So they actually told you already that omega square is rho Ag over m, but at the same time, you know omega is actually 2 pi over T. So you sub in for omega, you will be able to get the period. So 2 pi over T square equals to all the required values of density, area, gravitational acceleration divided by mass. You're going to get the period eventually as 0.853 seconds. So now T1 is half a period. You're going to get 0.427 seconds. All right? And when it's all done, and then T3, if you proceed with your calculations, T3 is actually 1.5 of your period. You're going to get the answer as 1.28 seconds. right? So that is what you're going to get for these two questions. Okay, so if that one is okay, then I move on to the last part of your question. Okay, the last part of your question asks you to find out the total loss in energy of the oscillating system between 0 and T4. What's the loss in total energy of the system between 0 and T4? So if you look at your graph right now, T equals to 0 is right over here. Hey, sorry, why am I using white color? T equals to 0 is right over here. T equals to 4 is right over here. Now, what you're supposed to do is to find out the energy at this point. Let's call this E1. And energy at this point, let's call this E2. Okay? Your energy loss is supposed to be E1 minus E2. Now, the energy at point 1 and point 2 here, you already learned that total energy is half m omega square x naught square. This one is the expression for total energy that you learn from the notes. So you are supposed to apply E total equals to that to point 1 and point 2. Okay, you know the mass, you know the omega, and then amplitude. You may think you know the value, but actually there is something a bit different about this graph, because your graph here, if you read carefully, this is a graph of distance h versus time. Okay, it is not a graph of displacement versus time. Okay, when you're talking about your x naught here is actually your amplitude. Okay, it must be measured from equilibrium. Okay, so you look at your graph right now. They say it is a graph of h versus t. Your h is actually from here to here. Okay, so the thing here is that h is measured from liquid surface, not equilibrium. Because if I say to you right now that say this one is equilibrium position, if the object was displaced and then released, the object will oscillate up and down. So it could go to a top position here, it could go to a bottom position here. So in that case, your h would just still be measured like this. This is your h. This is again your h. Okay, they're all measured with respect to your liquid surface, not from your equilibrium position. Okay, so the graph that you're having right here is actually a bit different than the one that you're supposed to see. It's not a displacement time graph. Displacement for your case is defined as distance from equilibrium. But here, your graph is actually not displacement time. It's height versus time. The height is not measured from equilibrium. It is measured from the water surface. So how then are you going to find the amplitude? Okay, so if you just read the graph as it is right now, is a graph of height versus time. You know this point here represents the amplitude, but the amplitude value is not 20 centimeter. That is not correct. Okay, so how am I going to find the amplitude? To find the amplitude, all you just need to do is that you take the I know that from here to here is going to be amplitude. To find the amplitude, all I just need to do is I take 20 centimeter minus 18 centimeter. Okay, you see this one here is not starting from 0, isn't it? So if I really want to get the amplitude, I just take the difference between this value and this value. Okay, So that one, my amplitude is now actually 2 centimeter, right? So to make sense of why is it like this, you can just think of it as this now. It could be that my water level is here, like this. At equilibrium, my object was somewhere here. This one was where, this one is say at equilibrium now. Okay, this is where H was 18 centimeter. Now at 20 centimeter, that would mean that I'm at a much larger height. That one would mean something like this. So this one is 20 centimeter. This one could be thought of as basically your bottom position. Okay, so to measure your amplitude, you're really interested in this one only. This one is supposed to be your amplitude. Okay, it's from bottom. It's the distance between your bottom and equilibrium position. So to get this distance, it's just basically 20 minus 18, giving you 2 centimeter. That's how you would actually interpret this. No? All right. So to get the amplitude, just take the difference between the two values for t equals to 0 as well as t equals to 4. Okay. So once you've done that, you should be able to start doing the question already. All right. Find out the respective values and the respective points. So total energy, as I mentioned, is half m omega square x naught square. You don't really need to write out that E total is K max. This one is unnecessary. So total energy loss is actually the total energy at 1 minus the total energy at 2. So it's going to be half m omega square x naught 1 square minus half m omega square x naught 2 square. And then eventually you're going to get this half m omega square because you factorize it out. Then bracket x naught square 1 minus x naught square 2. Now mass you already know is 70 grams. You just divide by 1000 to change it to kg. Now your omega, if you read your question just now, omega is actually omega square was actually kind of given to you already, where it is rho Ag over m. You can either use this to find your omega, or you can either just say omega square is actually 2 pi over t square. Okay, either one would actually be okay for you to use. In my case, I actually use 2 pi over t square because I already found out the period from the previous question. So just remember to square the term. Okay, then from there, all you just need to do is you go and find out your amplitude, square, and take the difference. Okay, so amplitude 1, amplitude x naught 1, the comma there is the thing that kind of makes the thing look very ugly, right? I can probably just say x naught 1 here is actually 2.2 centimeter. Just now I wrote it as 2 centimeter, right? That is actually not the accurate one. X naught 1 is 2.2 centimeter. X naught 2 is actually 1 centimeter. Okay. But remember to change them to meter. And then remember to square them. Okay. So this one is actually 20.2 minus 18. That's why it's 2.2 centimeter. And this one is 19 minus 18. That's why it's 1 centimeter. So change the change the amplitude values to meter and then square it. Eventually, you will get your final answer as 7.29 times 10 power minus 4 joules. Okay. So this one is for this question. Okay. So this one is all right. Then again, we move to another different question. So that one will be page 9. So have a look at page 9. Let me clear this one. Okay, have a look at page 9 of your worksheet. This one should be quite straightforward. This is March 16 P42. All right, an object of mass 80 grams oscillates with simple harmonic motion. Okay, mass 80 gram oscillating with simple harmonic motion. The variation in time t of the displacement x of the object is as shown here. From the graph, determine the amplitude and period of the oscillations. Okay, so this graph is pretty straightforward. There's no trick behind it. It's actually really your displacement versus time. Okay, this one is already measured from equilibrium, so no hidden tricks. So from this graph, find out the amplitude and period. This is something that you already kind of learned in AS last time. So this one is your period of 0.3 seconds. This one is your amplitude of 1.8 centimeters, sorry. Okay, so your answer being this. Okay, yeah, 0.3 second, make sure it's minimum 2 SF. All right. Okay, so this one is fine. Now part B, use your figure and your answer in in A to calculate the K of the object at time equals to 0.19 seconds. So this one, they are actually quite specific in telling you the time that they want the kinetic energy. They say they want it at 0.19 seconds, which is actually right over here. This one is 0.19 seconds. Maybe I better use black to highlight it. So 0.19 is right over here. Okay, right over here. All right, so they want the kinetic energy specifically at that time with that displacement. So here, this one, you're not talking about maximum KE anymore, because this one, you can see from here, your oscillation is not even at equilibrium in the first place. It is actually at some other displacement value. So you have to use the EK equation directly, which is actually half m omega square x naught square minus x square. All right. So since I know that t equals to 0.19 seconds, the amplitude is the displacement is negative 1.2 centimeter. I just sub in the value of x now. Remember to change it to meter. Okay. Right. Again, omega is not given, but you know you can find it from 2 pi over t, knowing the period now. Okay. Your amplitude is 0.18. This one is your amplitude at 0.18 centimeter. Sorry, not 0.18 centimeter. The amplitude is at 1.8 centimeter. Remember to change it to meter and then square it. All right. So you will eventually get your answer as 3.16 times 10 power minus 3 joules. Yeah, when you are talking about t equals to 0.19 second, and then you saw that there's a negative for your displacement, it actually kind of doesn't matter also, because eventually you square it, so the negative will actually disappear. All right. So that's why here you notice that I kind of just wrote 0.018 square minus 0.012 square. I didn't really show the negative inside, because I know that once I square, the negative sign will be gone in the first place. So there's no need to show. All right. So that one should be okay, right? Okay, so this question is done. This is page 9. Then let's move on to page 10, which is the next page of your worksheet. Okay, so let's move to page 10. Okay, page 10 of your worksheet. This one is June 16 P41. Question 3a. Now state by reference to displacement what is meant by simple harmonic motion is the same thing that we've been doing the past two questions. So periodic motion in which acceleration is directly proportional to displacement for a fixed point and is always directed towards that point. Okay, just copy the definition from the notes and you should be okay. Now part B, a mass is undergoing oscillations in the vertical plane. The variation with displacement x of the acceleration a of the mass is as shown. Now state two reasons why the motion of the mass is not simple harmonic. Now by looking at this graph, how do I know that this motion is actually not SHM? So just now I specifically mentioned to you, if we follow simple harmonic, it will follow this equation. And then the graph of displacement versus time, sorry, not the graph of displacement, the graph of acceleration versus displacement, sorry, the graph of acceleration versus displacement would just be a straight line graph that passes through the origin. Okay, where you are supposed to get, if you are at x naught, you're going to get negative a max. And then when you're at negative x naught, you're supposed to get positive a max. This is the graph that you're supposed to get. So looking at your current graph in the question, you can actually see that it's actually no way the same as what I just drawn on the screen, right? So what could be the two reasons why this is not simple harmonic motion? All right. So the first one that you can probably talk about is actually point number 2 here. You see, if I try to use my ruler and I try to align it according to the given line, you see that it's actually not a straight line. It kind of curves off somewhere. Maybe if I try to draw a straight line here like this, you see that it isn't following a straight line. There's some curvature away from the straight line. So what I can say here is that in the first place, the graph is curved, it's not a straight line. So when the graph is curved, it's not a straight line. This means that acceleration and displacement are not proportional to each other. Okay. Now, in your case, your question is really just asking you to state what is it that tells you that this is not simple harmonic motion. They didn't ask you to explain. If they ask you to explain, it will be the statement in red. Okay. This one is state. The first sentence here is state. The second sentence in red is explaining. Okay, but your question here doesn't require you to explain. So you really just need to put the stating part only. But in my case, for the sake of completeness, I just explain also. All right. Okay, so graph is curved, not a straight line. That's the first thing that tells you that it's not simple harmonic motion. What is the second thing that tells you that it's not simple harmonic motion? Right? Now, when you look at the graph for acceleration versus displacement, you can see that the graph is actually kind of symmetrical. Okay, it's symmetrical. So how are you going to word your questions? How are you going to word your answer with respect to this question? Because when you see your graph here, you can see that this part is actually not really the same as this part. They're not symmetrical, all right? But instead of using the term symmetrical, how are you going to word it properly? You can actually say this. You see that the maximum displacements and accelerations are different, okay? When the maximum accelerations and displacement are the same, that's what got you your symmetrical graph in the first place. So in order to explain it, you just say maximum displacement and accelerations are different here for both the graphs. For the graph itself. Okay, the maximum acceleration and displacement here is different than the maximum acceleration displacement here. So therefore, it is not simple harmonic motion. By right, they should be the same for SHM. Okay, so in SHM, both sides of the graph should have equal maximum displacement and acceleration. Okay. Okay, so this one is fine. Then we move to another different part. Let me just clear this one off. Okay, now look at part C. Part C is telling you that you have a block of wood that's floating in the liquid as shown. It's kind of like the question that we did just now, where you have a tube that's actually floating in some sort of liquid. Now they replace it with a block. The block is displaced vertically and then released. The variation with time here, the displacement of the block form equilibrium position as shown. Okay, now this one you see, they are really just giving you a graph of displacement from equilibrium versus time. Okay, so this one is a pretty straightforward graph, not like the one before where it is actually not measured from equilibrium. This one is actually measured from equilibrium. All right, so use the graph to determine the angular frequency omega of the oscillation. So this one, when you look at the graph, you know that omega must be 2 pi over t. You just find out what is the period in the first place. The period is actually 0.8 seconds. So use that value, 2 pi over 0.8, you're going to get the answer as 7.85 radians per second. Okay. Right. So that one is done. And next one should be next page. Okay, find out the maximum vertical acceleration of the block. If I want to find out the maximum vertical acceleration of the block, I can actually just straight away say that A max is equals to omega square x naught. Okay. Now this one here is kind of like just showing you how the thing was derived. You actually don't need to show this. This is actually not necessary. Okay. You can straight away just say A max is omega square x naught. So omega, you already found out from part 1. Just sub the value in, square it, and then multiply with your amplitude. Okay. Now your amplitude, you need to use this one. Okay. A max is omega square x naught. To get A max, your amplitude must be maximum. Use amplitude maximum. Okay, use maximum amplitude. Use the max amplitude, because you see sometimes when people do this question, you see that there are multiple values of amplitude, right? The amplitude values are not the same throughout the oscillation. So which one should you actually pick? You should actually pick the one with the largest value, which is this one, because you want maximum acceleration. So you pick the largest amplitude that you can find, which is this one. Some people had a tendency to pick this one. This is not correct because this is not the largest amplitude. The largest amplitude is the one at the bottom here. Okay, so pick that value and then you eventually get your answer as 0.924 meter per second squared. Okay, that's how you get your answer from that. Okay, then another last thing to do would be finding the energy loss again. Now the block has a mass of 120 grams. The oscillations of the block are damped. Calculate the loss in energy of oscillations of the block during the first 3 complete periods of its oscillations. So what is the total amount of energy loss for the first 3 complete periods of oscillation? Okay, so here, if you look at your graph, this is the first oscillation. This is the second oscillation. This is your third oscillation. So you're really trying to find the loss in energy from here and here, between these 2 points. So total energy is going to be half m omega square x naught square. You apply to this point as well as this point. Okay, and here this one is pretty straightforward because your really getting a displacement versus time graph. So whatever you read here is your displacement value itself. Sorry, whatever you read here and here is your amplitude value itself. There's no subtraction whatsoever required. Okay. So here you just sub in your values. You say the loss in energy is ET1 minus ET2, so it's half m omega square x naught 1 square x naught 2 square. Right? And then after that, you're going to get half 0.12 times 7.85 square multiplied with 1.5 centimeters square minus 0.9 centimeters square. But remember to change that to meter in the first place. Okay. Then your final answer should thus then be 5.32 times 10 power minus 4 joules. Okay. All right. Now, some students have asked me before, do I need to write all these things here? Can I just kind of like just substitute everything in one shot like this? You can actually do so, okay? If you want to just substitute all the values in one shot rather than just showing the equation, where it came from before submitting your values. So what I'll mention is just this now. The first part here, this one ET is equals to K mass half m omega square x naught square. This one actually you don't need to show. This one is not required. But this one here is recommended to show. Okay, recommended to show, because what if you substituted the wrong values? Okay, see, because your marks are C1 marks, they are C marks. Okay, C mark is basically a mark where it doesn't need to be explicitly shown in your workings. It must be implied from your workings. Okay, let's say for example, if I look at my workings right now, I see this equation, I see all these values here in the equation. This implies to me I already know half m omega square x naught 1 square minus x naught 2 square. All right, so if I did not show this, and then I go and show just this alone, I will have still gotten the C mark from here, because this working here is implying that I know this equation. Okay, but what if, say for example, in the process of substituting this the values inside the equation right over here, in the process of substituting the values of the equation right inside here, I somehow substituted some value here which is wrong. It's a careless mistake. Let's say, for example, you substituted in some sort of random value, say maybe 8.5, and then you forgot to square it. So from here, the examiner will be wondering, whether do you actually know the correct equation, or do you actually interpret it as just half m omega x naught 1 square minus x naught 2 square. So here, in such a case, because you substituted it wrongly here, you not only will not get the mark for this, you also will not get the mark from this. Because here, if you just show this one right here, it did not imply that you know this, because your values here cause some sort of ambiguity where the examiner will be thinking either you know this or either you thought it was this. So they cannot decide, they will just minus off your mark, because they by default they'll say, oh, you probably thought it is this. That's why I say it's recommended that you show this. Okay, although it's not required, but it's recommended, just in case when you substitute in your values and then somehow you made some careless mistake, at the very least the examiner knows that you know the correct equation to use. Okay, have a look at page 18. It involves calculation and graph drawings again, but the beginning of the question is actually in page 17, sorry. So if you just have a look at November 16 P42, Okay, so for this particular question here, they mentioned that you have a mass that hangs vertically from a fixed point by means of a spring as shown in the figure below. The mass is displaced vertically and then released. The subsequent oscillations of the mass are simple harmonic. And from here, the variation with time t of the length L of the spring is as shown in the figure below. So this is the graph that you are having right now. Okay, so for the graph that you're having right now, be careful about the graph that they give you. Always try to look whether it's a proper displacement versus time graph. In your case here, the graph that's just been given to you, it has the characteristic sinusoidal shape showing that it's an oscillation. But look at the axis of the graph. This one is actually length over time. Okay, so it is actually not really a graph of displacement versus time. Instead, it is actually length versus time. So your length here is this one. It is actually not measured from equilibrium, but from where this one is, it looks like the ceiling, but it's not correct to say it's the ceiling. Okay, but from another fixed point, okay, from another fixed point. Okay, it's better to probably say this. All right, so your current case is that this length L is actually not really measured from equilibrium, but it's actually from another fixed point. This is actually the fixed point from which your length measurement is taken. All right, so if you imagine that this one is your equilibrium position, as your mass oscillates up and down, it will eventually touch the top position here, and then it will eventually touch the bottom position here. So if let's say it was at the top position, this one will be the length at the top. This one will be the length at the top. And if it was at the bottom position, this one will be the length at the bottom. Okay. And then this one will be the length at equilibrium. Okay. So as it oscillates up and down, you will have different lengths. Okay. So they try to measure the length with respect to time. This is the question that you're getting. All right. Now from that figure itself, state two values of t at which the mass is moving downwards with maximum speed, right? So from last week's lesson, I mentioned to you that max speed is always at equilibrium position. In your case, it will either be up or down. Okay, it will always be maximum speed at equilibrium position, and you will have two different directions, either it's up or down. Okay, but now if you look at your graph right now, knowing that this is actually a length versus time graph instead of displacement versus time graph, you kind of need to identify what are your equilibrium positions, what are your top and bottom positions. So here, if you look at this line, the 17 centimeter mark, you may be tempted to say that this is actually the top position. But this is actually not supposed to be the top position. This is actually the bottom position. Because if you imagine this, if your mass is actually oscillating up and down, when it's at the bottommost position, the length is actually the longest, which is here. So this is actually supposed to be bottom. Now conversely, if you're talking about this position here, you see this one is the lowest length value. Now the lowest length value ought to be when you are at the top position, because it makes sense, right? If you are at this top position here, your length measured from the fixed point at the top here would actually be the shortest. So this one is actually your top position. Okay, so the middle between the top and bottom ought to be your equilibrium. So if this is 17 and then this one is 13, right in the middle of it is your equilibrium position. So it will actually be at the 15 centimeter mark. This is where your equilibrium position is. Okay, and then this one is actually your top position. Okay, so how do you know it's actually 15 for the equilibrium position? You just take 17 minus 13 divided by 2. You're going to get the answer as 15. Okay, so that's how I know that it's 15 here. So I know that my max speed is at equilibrium position. It will either be here, 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 or here. Okay, but knowing that when you are equilibrium position, your speed can either be outwards or downwards. So which is which now? So you see here, this one is from bottom going to the top. This one is actually going up. This one is from top going to bottom. This is actually going down. And then this one is the same now. From bottom to top, this is going up. And then this one is from top going to bottom. This one is going down. So the one that is actually maximum speed going downwards is actually this one and this one. So the time would actually be this one 0.225 and then this one 0.525 seconds. Okay, so this is the positions in which you would have your masses going downwards with maximum speed, right? So if this one is okay, then I will move on to the next subsequent question. All right. All right, so next subsequent question will be this one. Now, determine for these oscillations the angular frequency omega. Now, angular frequency omega, you by now should know that omega is 2 pi over t. You really just need to find out the period. Your period is 0.3. So take 2 pi divided by 0.3, you're going to get the answer as 20.9 radians per second. Okay, so your graph here, if you just look at it, this one is strictly speaking your period. Okay, t is equals to 0.3 seconds. Okay, so just take that value there and then divide by take 2 pi divided by 0.3, you're going to get the answer as 20.9 radians per second. Okay, so this one should be fine. And then the next one is show that the maximum speed of the mass is 0.42 meter per second. Okay, so keyword here is maximum speed. If you want maximum speed, it's already mentioned to you, you just need to take omega x naught. Okay, you don't need to know, you don't really need to show the derivation. You can just straight away write this equation whenever you see that they ask you to find out the maximum speed. So Vmax is omega x naught, then x naught here being your amplitude position, amplitude value, you just take 20.9 from above and then multiply with your amplitude. Okay, so your amplitude here, this is something that you need to be careful about. Remember just now I told you that this is not your displacement time graph, it's rather your displacement, it's rather your length versus time graph. So there were certain points of interest here that I actually mark out for you, where I tell you that this one is actually the bottom, this is the equilibrium, and then this is the top. So you want to find the amplitude position, you either be this one or this one. Okay, so this is the amplitude that you want. So you just take your values accordingly. You either is you take 17 minus 15 or you take 15 minus 13. You should be getting 2 centimeter as the amplitude. Okay, so just pick whichever you like. In my case, I actually took the top position to the equilibrium. So it's 17 minus 5, but because it's in centimeter, remember to change it to meter. Okay, so your final answer eventually would be 0.418 meter per second. Round it up to 2 SF to match the answer inside the question. Right? So that one is okay. Then I just clear off this diagram again. Now, for part B, use your data from the figure and A3 to sketch on the given axis of the graph below the variation with displacement x from equilibrium position of the velocity v of the mass. Okay, so here they're actually asking you to sketch a graph of v versus x, acceleration versus displacement. So that time we mentioned that when you have something like a graph of v versus x, v versus displacement, it's generally going to be a shape that looks like this. It's either a circle or an oval shape. Whether it's a circle, whether it's an oval, it depends on the scale of the graph that's given, but generally it should be a curve, okay, not a straight line. So there were a few points of interest that I mentioned to you. V is 0 at amplitude, and then V is max at equilibrium. And then you have, it has two directions. Okay, so when you talk about V is max at equilibrium, I mentioned that it has two directions, positive or negative. All right, so looking at it right now, we know that our amplitude position is 2 centimeter. So at amplitude plus minus 2 centimeter, V is 0, which is here. Okay, and then for our case, when x is 0, our velocity will be positive, negative 0.42 meter per second. Okay, meter per second, not meter per second square, meter per second, which will be this one and this one. Okay, so just draw those 4 points, and then after that, it's a simple matter of just joining the points together. So you just plot the points and then join them together. Okay, now if let's just say you don't have a compass or whatsoever, one of the few things I noticed is that will make your curve drawing easier is that I'm sure you have your plastic 15 centimeter ruler, right? So what usually helps is that you just take your plastic centimeter ruler, you curve your plastic centimeter ruler according to these 2 points, and then you just draw the line. And then you repeat for the subsequent sections. You ought to be able to get a nice curve. Okay, that's how I would do it nowadays. All right, so that is for this question. Okay, so this question is okay. Then I move on to the next subsequent one. This one is page 18. Next one will be page 25. Okay, so have a look at page 25 of your worksheet. There's only 2 more questions to go before I move on to the next part of your notes. Okay, so have a look at page 25. All right. So for page 25, this one is November 17, P41. Okay, so if this is November 17, P41, okay, now by reference to simple harmonic motion, what is actually meant by angular frequency? So this is a definition of angular frequency. Angular frequency is just simply frequency expressed in terms of radians per second. It's a definition that you already have written inside your notes. Now, if you want to write it in the form of an equation, just write it in word equation forms like this, where you say angular frequency is equals to 2 pi times frequency. So I think I mentioned this before. Don't just write something like this without explaining the symbols. Okay, so you kind of like just wrote this 2 pi f without even telling us what was actually omega, what was actually f. This one will actually be incorrect. Okay, so write it in words now. Write the full terms out. Okay, then for B, a thin metal strip is clamped at one end so that it's horizontal. A load of mass m is attached to its free end. The load causes a displacement s of the end of the strip as shown from figure 2.1. The load is displaced vertically and then released. The load oscillates. The variation with acceleration a of the displacement a of the load is shown in this figure here. Okay. So this is what you have. And you see this graph looks like this right now. Now the graph that you are used to seeing when it comes to acceleration versus displacement was something that looked like this originally. Okay, this was the graph that you were used to seeing when it came to acceleration versus displacement. It's a straight line graph that passes through the origin with negative gradient. Remember? So here you are seeing a somewhat similar shape of your graph, but somehow something feels off, isn't it? So you see in the left diagram, your acceleration is 0 when x is 0. But here, when your acceleration is 0, you somehow have some displacement value. So what is actually happening here? And also notice that your graph axes are actually kind of inverted. This one was acceleration on the y-axis, displacement from equilibrium on the x-axis. But the current graph that you have is the other way around. Is your displacement s on the y-axis, but acceleration on the x-axis. And then not only that, somehow or another, when your acceleration is 0, you have some value of displacement. So something feels off here. You kind of need to read carefully what is this displacement really is. And what is this displacement really about? If you refer back to your question, your displacement S is defined here. Okay, you read one statement before this, they told you that a thin metal strip is clamped at one end so that it's horizontal. So originally, it was supposed to be like this. But then what happened is that you go and attach a mass at the free end, meaning to say you attach something right over here right now. And that mass that you attach cause your beam to actually bend. So while originally it was like this, it has now suddenly bent like this as a result of you applying your load here. Okay, this one here, you can think of it as your equilibrium position right now. Okay, so when you attach your mass m towards the at the free end of the beam, it causes the beam to bend downwards and then reach some sort of equilibrium position. So once it reaches this equilibrium position, you actually measure the displacement, but this displacement isn't the displacement that you are used to seeing. The displacement that we were always interested in was displacement from equilibrium. But this displacement that you're seeing right over here is actually not displacement from equilibrium. This is actually displacement from unloaded position. Okay, so while they've been using the term displacement here, this is not the displacement that we are really interested in. We are not interested in the displacement from the unloaded position. what we are really interested in is supposed to be the displacement from equilibrium. Okay, so that kind of explains to you why your graph shape here kind of looks weird, because your displacement here is a different kind of displacement. It's actually measured from a different fixed point other than your equilibrium. All right, so if your mass is already equilibrium at this particular point here, logic would tell you if you somehow displace the mass and then you release it, your mass will oscillate up and down. No? It will oscillate up, it will oscillate down. And then at those respective positions, you will again measure their displacement. But your displacement is again measured from the unloaded position. Okay? So that's how you got this graph here. All right? Just so you understand. All right? It's actually still the same graph, just that it's actually being drawn a different way because you define displacement slightly differently. Okay, so if you look at the next page, they're asking you, use that figure that they've just given you to determine the displacement of the load before it's made to oscillate. So what is actually the displacement of the load from the unloaded position before you actually made it to oscillate? Okay, meaning to say they want this one. If you are at equilibrium position now, what is actually your displacement from the unloaded position? Okay, they want this one. Okay, so you just read the value from the graph. We know that in your case, at equilibrium, acceleration is 0, right? You can actually see it from your current graph here. When your acceleration is 0, your value of s is actually 2. So this is actually the equilibrium position. This is actually your equilibrium position, the displacement at equilibrium position, because here your acceleration is 0. Okay, so your answer for that question is that your displacement is 2 centimeter. Okay, and then the next thing they'll ask you is find out what is the amplitude of oscillation of your load. So if you displace the mass and then you release it so that it starts oscillating, what is now the amplitude of oscillations of the load? So again, you refer back to the graph. If you look at the graph right now, you can also kind of say that at amplitude, A is max. Okay, this one is also something that you would have realized by now. At amplitude, A is max. So you look at your graph, this part here is where you have positive A max. This part here is where you have negative A max. So these are the positions of your amplitude. These are the positions where you are having your amplitude. Okay, this is your amplitude position. All right. So this one and this one. Okay, so maybe I need to delete this. Yeah. So this part and this part is where you have your amplitude. Okay. So now you want to find out your amplitude values. This one, what you need to do is something like this. They're asking you for your amplitude right now, but recall that your amplitude is measured from equilibrium, not from some arbitrary reference point. Okay, whatever you have here is measured from unloaded position. Okay, so you cannot actually just simply read the amplitude value from here or here. Okay, because it was not even measured from your equilibrium position. So you actually have to do some further calculation to get your amplitude position. So in your case, your amplitude is actually this one. Sorry, it's actually from here to here or here to here. This is your actual amplitude. Maybe it's better if I just write it as this. This one is your equilibrium position. This is your amplitude position. And then this is also amplitude position. But if you really want to get amplitude, this one is your amplitude. Okay, so you just find those values there. In my case, I cannot really read the graph properly because my values are, my writing is obscuring the graph. Eventually, you read the graph values properly and you take the difference between the equilibrium and the amplitude position, you should get your amplitude value as 1.5 centimeter. Okay, it should give you 1.5 centimeter. Okay, if you try to read the values on the graph properly and take the difference, you ought to get 1.5 centimeter. So in your case, if the answer is 1.5 centimeter, this one ought to have been 3.5 minus 2. And then this one ought to have been negative, sorry, this one is not negative. This one would have been 2.0 minus 0.5, giving me 1.5 centimeter. Okay, this is your amplitude position. Sorry, this is your amplitude value. Okay, so far so good with this. All right. Okay, so that one is for that graph. Then we move on to the other part. So let me just clear off the drawing again. Now, show that the load is actually undergoing simple harmonic motion. How do I know that your load is actually going simple harmonic motion? So in my case, that time I kind of mentioned to you before inside the notes, you can actually deduce whether something is undergoing simple harmonic motion by just looking at the diagram. If it's an acceleration versus displacement graph. So if you have an acceleration versus displacement graph like this, I specifically mentioned that the graph shape can tell you that you're undergoing simple harmonic motion. There are two things that you will normally look for. The first one is this. You say straight line through origin shows that acceleration is directly proportional to displacement. Maybe I write this in full form. That acceleration is proportional to displacement. Okay, is referring to this one. Straight line through origin shows you that acceleration is directly proportional to displacement. And then the second thing that you tend to look for is the gradient. Okay, so if you see negative gradient shows that acceleration and displacement are always in opposite direction. Okay, so in the form of a diagram, these are the two things that you tend to look for. See there is a straight line, see there is a negative gradient. So from here you can then conclude that therefore it's simple harmonic motion. Okay, so here when they ask you to prove from your graph that your load, here they didn't really ask you to specifically relate to the graph, but it's really implied, show that the load is undergoing simple harmonic motion. You can actually deduce this from the given graph. Okay, so the graph that was given to you look like this, isn't it? This one was your This one was your displacement S versus A graph, and then they give you something that look like this, right? So you would try to put these 2 points into your answer, but how do you go and actually relate it to your current graph here? Because you see your current graph here is not strictly speaking a acceleration versus displacement graph. The displacement is a different kind of displacement. So if you try to put this answer in directly into your question, there's something else you need to write first. That one is actually this one. This graph shows the variation of displacement from equilibrium. Okay, now rather than saying showing, it's probably better to show this graph indicates the variation of displacement from equilibrium with time. Sorry, not with time. It shows the variation of displacement with equilibrium. It shows the variation of displacement with acceleration of the mass. Of the mass or of the beam. Let me see what I call it. Displacement S of the load. Okay, sorry. This graph indicates the ratio of displacement from equilibrium with acceleration of the load. Okay. So if you have this statement, it kind of implies that this graph is similar to this graph here. Okay. That's why you see here your question actually has 3 marks allocated to it. You're actually supposed to kind of write some sort of statement to describe that this graph is actually similar to this. So if you want to write that statement to relate them, it will probably be good to write the ones that I've just written here for you. This graph indicates the variation of displacement from equilibrium with acceleration of the load. Okay. The written answer from the work solution says this now. The graph shows variation of acceleration and displacement of the load as it oscillates about the equilibrium position at s equals to 2 centimeter. It's actually the same thing, but somehow or another, this one feels a bit wordy. And you when people read this, they don't know why on earth did I actually write this. Okay, so I think it's better if you just write this. The marking scheme itself was actually equally confusing. They actually didn't really say much. They just said this. I mean, if you just read the marking scheme, for the 3 marks that were given to you, they just say reference to displacement or oscillations, or displacement for equilibrium position, or displacement from 2 centimeter. That was the first point they want. Then after that, they say, okay, then you say the straight line indicates acceleration is proportional to displacement. The negative gradient shows acceleration and displacement are in opposite directions. Okay, so here, you just basically need to write this first point here. Okay, then after that, you relate to the 2 points that I just mentioned on the right here. Okay, now you need to adapt one of your answers to suit the given graph. You see, for my case here, I say straight line through origin shows that acceleration is directly proportional to displacement. Your graph here that is inside the question doesn't really pass through your origin, so it's actually not accurate to say it passes through the origin. It would be sufficient for you to just say that straight line indicates acceleration is directly proportional to displacement. Don't write through origin because that is for acceleration versus displacement graph, where displacement is from equilibrium. This is not the proper graph that you're referring to. Okay, the question gave you a different kind of graph with a different kind of displacement. All right, so this one is 1 point. Then the other point would be you just saying the negative gradient indicates that acceleration and displacement are always in opposite directions. This one I can just directly copy the ones on the right, okay, without changing anything. So in your case, first point, second point, third point. That's where your 3 marks come from. Okay. So far so good for this. All right. Okay, so if you're all right with this, then the next part of the question is asking you to calculate the frequency or oscillation of your load. Okay. Now, in your case here, the one that's written inside your work solutions is trying to relate your graph to a straight line equation, where here I say that A is equals to negative omega square x, then after that x is equals to negative 1 over omega square A, and then we're trying to relate this to y equals to mx plus c. I can actually see that, yeah, the x-axis would actually be, sorry, the y-axis will actually be displacement, the x-axis will actually be acceleration. From there, subsequently, gradient is actually negative 1 over omega square. So the subsequent workings that you see here is just you trying to calculate the gradient and then equating it to 1 over omega square. And then finally, you say that omega is 2 pi f square, or omega is 2 pi f. Then because you have a square term here, you also square the 2 pi f equal to this. Then finally, f is 1.23 hertz. Okay, so this one seems a bit convoluted. It seems a bit complicated to do. This one is one way of doing it. This one is using gradient. You can actually use another way. You can use single point substitution. So here, rather than doing something as complicated as this, you can actually just say, what if I just say A is negative omega square x? Now, just now you actually already did find certain things from your graph. You actually already found out your amplitude value as 1.5, right? So your when x is amplitude, when x is equals to your amplitude is equal to your amplitude at 1.5 centimeter, what was the value of your A from your graph? If you look at the value of A from your graph, let me just erase everything else here. If you look at the value of your amplitude, at this value, this one here, just now I told you is actually your amplitude position. Okay, when you work out the values of the amplitude value from there, from here you can actually try and see your value of your acceleration. Okay, so in your case you should get some values, but I'm having difficulty seeing that value right now. Wait on, let me see this. Let me erase this. If you're talking about this one here, it's right smack in the middle here. Yeah, so this one is, if you try to see from here, this one requires you to read the graph properly. So here you have 0.2 divided by 5, each one is 0.04. This one here is actually negative 0.84, 0.88, 0.92, 0.96, and 1. This one is actually 8884, sorry, 8488, or 0.9. This one is negative 0.90 meter per second square. Okay, you try to read it properly lah. So A here is actually supposed to give you a value of 0.90 meter per second square, right? So what you could have done is that from here, if you already know the amplitude value, and then you already know the acceleration value corresponding to your amplitude, you could have just straight away use this equation sub it in, you get 0.90 equals to negative. Okay, now just omit out the negative because you don't really want to bother about that. You get 2 pi f squared times with 1.5 times 10 power minus 2. So you just do whatever you need to. 0.9 divided by 1.5 divided by 10 power minus 2 divided by 4 pi square. Then square root of the answer. Your frequency will be 1.23 hertz. Same like what you have right over here by calculating the gradient. But you see, when you do this one here, this one is so much simpler than you calculating your gradient. Okay, so you can use single point substitution. Okay, now single point substitution, you don't necessarily need to limit yourself to finding the values at the ends here. Okay, you can actually use any point on the graph. You will be able to get the answer. So this one, single point substitution, use any point on your graph. Okay, any point would do. Okay, you don't necessarily need to pick the value at amplitude. You can pick somewhere in between. All right.